In this video, let's look at something called the chi-square statistic, which is going to be used to measure if distributions are around what we expect to see. And so this symbol right here, by the way, this is just the Greek letter chi, perhaps a little bit poorly drawn. But anyway, that's what it is. So let's start with a problem that we might want to solve using a chi-square statistic. So let's say I have some dice here, and maybe there's a particular die, and I want to find out if it's fair. And so what I could do is just roll the die a bunch of times, and each time I roll the die, I could record the outcome. And so let's suppose after maybe 36 rolls of the die, right? Let's suppose this is what happened. After 36 rolls, I got 4 1s, I got 8 2s, 5 3s, 10 4s, 3 5s, and 6 6s. Okay. So what we need is to determine, one, what did we expect to see here? And then number two is this far enough away from what I expected that maybe I should be curious about, if this die is weighted correctly or something like that, right? So let's start out with, what did we expect to see? Okay, and in this particular case, what I expected to see, right, if I did 36 rolls and I have 6 bins, so this is what I observed, but what I expected to see is just 36 divided by 6, and I would get, right, I expected to see 6 of each thing. Now, when I say expected, I mean this is just, how many ones, on average, how many ones would I see? 6. On average, how many 2s would I see? 6 if I were to repeat this experiment over and over again. But what I do know is that, hey, in life, when you do things randomly, they don't work out perfectly, even every single time. So, I expected 6 things, but what I really mean by expected is, I expected to see approximately 6 in every bin. I don't expect to see anything too far higher than 6, or anything too far lower than 6, and all these numbers will be reasonably close together, right? That's what I expected to see. And so now we can measure how out of whack is this distribution of outcomes from what we expected to see. And for that, we're going to use the chi-square statistic, which is just this. So it's chi-square, and it's a summation. So this is the Greek letter sigma, which means it's a summation. And I'm going to do the observed value minus the expected value. I'm going to square that and put it over the expected. Right? And so this is real easy to calculate. If this formula doesn't make sense now, it will as soon as you see the math worked out. So chi-squared. And in the first case, I observed 4, but I expected 6. And I'll square that, and I'll put it over the expected. For the 2s, I observed 8, even though I expected 6. And then I observed 5 3s, I expected 6. And then, let's see, 10 minus 6 squared over 6 plus 3 minus 6 squared over 6 plus 6 minus 6 squared over 6. All right, so this is the formula. And so we'll just work this out. The numbers are nice and tiny, so we can just do this in our heads. 4 minus 6 is negative 2, but when we square it, we get 4. So we got 4 6. And here, 8 minus 6 is 2, squared is 4, so we get 4 6. And let's see, we got negative 1 squared, that's 1 6. Here we have 10 minus 6, so that's 4 6 squared, so that's 16 6 plus, let's see, negative 3 squared is 9 6. And then 6 minus 6 is 0, so that's 0 6. And we'll go ahead and add all these up. And so we got 4 plus 4 is 8, 9 plus 16 is 25, plus 9 is 34 sixths. And so this is about 5.67. So this number here measures how far this distribution of values is away from what we expected. All right, so now that's kind of a weird thing to say because like 5.67 what, and it's 5.67. I don't know, average of squared differences. It's nothing. It's not really a meaningful number. So if I told you some distribution had a chi-square of 5.67 without any context to it about where the numbers came from and about how many bins there were to divide things up in, how many categories there were, this number would be meaningless. But we can kind of figure out what it means just by thinking about what would happen if the numbers changed. And actually, we could start out by looking at like, why are we squaring in our formula? And so let's imagine we didn't square, and let's think about what would happen. And so if I got, so for here I have my 4 minus 6, and I would get negative 2, and I would have negative 2/6. And here I would have 8 minus 6, and that would be 2/6. And when I add those together, I would have a negative 2/6 plus a 2/6, and they would cancel each other out. And in fact, what's going to happen is, right, so 5 minus 6, well, that's negative 1. That means something else over here has to be at least 1 bigger to balance that, right, to balance that out. And so without squaring, if I didn't do squaring, what would happen is for all of the values that are below, there needs to be something above that corresponds to it, to balance out the distribution. And so without squaring, we'd always get a chi-square of 0, right? So by squaring, what we did is we made all of our differences from what was expected positive, and therefore we can add them up and we get a better sense of how far things deviate from what was expected. The other thing that happens by squaring is that we magnify the effect of outliers on this number right here. So like, let's take a number like 5, which was 1 away from what was expected, so it contributed 1/6 from the sum. Now this, the 8, which was 2 away from what was expected, notice how it didn't contribute 2/6 to the sum, it contributed 4/6 to the sum, right? So, and then here we have a value that's 4 away from what was expected, and yet it contributed 16/6 to the sum. And so, right, the further a value is away from what is expected, the more it contributes to this sum. And what that, so you can kind of see that if all of the values are really, really close to what was expected, this value is going to work out tiny. And if some of the values are significantly different from what was expected, it's going to make this number grow. So this number 5.67 on its own is meaningless, but if I were going to do another experiment with die rolls, all right, the more out of whack this distribution got from what I expected, the bigger this number would be. And if I got a distribution that was close to what was expected, right, this number would be tiny. And in fact, like if I got straight 6s across, you could probably see that the chi-square would just work out to 0. Now, that would actually be kind of weird too. I wouldn't expect to see that happen. But anyway, that's another story. But anyway, right, what we should look at here is just have this general sense that when you repeat the same experiment over and over again and you compare chi-square values, right, the more out of whack distributions will end up with larger chi-square values, and the closer, the distributions that are closer to what expected will have smaller chi-square values. One more note here is that this 36 rolls really isn't enough to draw any meaningful conclusions from. I used a tiny sample here and tiny numbers just because it made the math easy to work out by hand. But with 36, like we expect these things to come out rough, all these numbers to be roughly even. But after doing it 36 times, we really haven't given enough time for all the randomness to, let's say, work itself out. And so, in small samples, sometimes weird things happen, whereas if you were to keep repeating trials, randomness would sort of balance out. So anyway, this is a good example for showing the procedure, but just understand that maybe this experiment, if I really wanted to get something meaningful out of this, I should probably be rolling maybe 100 times at least or something like that, and then this number would be a little bit more reliable. And the other one is, this chi-square statistic, right? I would only compare the chi-square statistic for something with 6 bins to another experiment that had 6 bins, right? 6 possible outcomes to put numbers in here. So, if you think about it, like if you had a 12-sided die, perhaps, and you repeated the same experiment, right? You would end up with 12 terms in your sum, and the chi-square would just almost necessarily be bigger just because we added more terms together. So I would only compare a 6-outcome distribution with another 6-outcome distribution, and I will only compare a 12-outcome distribution with another 12-outcome distribution, if I was going to directly compare these chi-square values. Now, there are ways to look at chi-square values and compare, experiments that have different numbers of outcomes in it, but that's right beyond the scope of this video. All right, and I guess my final note here is like, 5.67, does this mean anything? And not really. Does it mean that this die is, perhaps unbalanced? And probably not, right? So I looked up on a table, like, how weird is the 5.67 chi-square value if there's 6 outcomes, and it turns out that a distribution this far from just straight 6s is going to occur about 34% of the time, so that's not really particularly unusual. And again, this little number here, not important for you to understand where that came from, right? Again, we're just looking at the more out of whack things get, this number gets bigger, and the closer to what expected occurred, this number remains reasonably small. All right, so that's it. And we could go further with this with different times, with different types of experiments, but right, as long as you understand what's generally happening with this number, that's good enough for now. All right, if you have any questions, let me know.